Imagine a tiny flicker in the dark. Not loud, not urgent, just a small glimmer that appears, hums for a moment, and quietly begins to drift. That's light, and it has been moving like this, calmly and endlessly, since the universe was born. Not in a rush, not in a frenzy, but always forward, never resting, never late. You've seen it 1,000 times, through a crack in the curtain at dawn, reflecting in puddles after rain, dancing across your ceiling in the afternoon. But have you ever asked what it truly is? What carries that warmth to your face on a winter morning? What threads the sky to your eye when you look up at the stars? That little flicker is more than just illumination. It is the pace at which the universe speaks. Light isn't something you can hold. If you reached out your hand to grasp it, it would already be gone, not because it's hiding, but because it was never really still. Light is a traveler, not a person or a vehicle, but something even simpler, stranger. A photon, a name for something so small and massless it has no sense of rest, no time to sit down, no place to settle. It's not even quite a particle, not really a wave either. It moves like a wave, with frequency and rhythm, yet arrives like a particle in discrete little packets of energy. That contradiction should bother us, but instead, it just rocks us gently into curiosity. If you were to imagine the universe like a vast and empty lake, perfectly still, with nothing but silence pressing in from all directions, light would be the first ripple. It wouldn't need anything to push off from. No paddle, no boat, not even the wind. Just the trembling of electric and magnetic fields twisting around one another like two invisible ribbons wrapping endlessly, creating a motion that sustains itself. This dance, a wave that moves forward without needing water, without needing air, is how light carries its message across the void. And how fast does it go? The number is oddly precise, 299,792,458 meters per second. But don't worry about remembering it. It's enough to know it's unimaginably swift. If you had the entire circumference of the Earth stretched out like a running track, a single beam of light could circle it more than 7 times in 1 second, not 7 laps in a minute, in one heartbeat. The moment you blink, it's already returned, run the race again, and whispered to the moon on its way by. But light isn't always in a hurry. That speed, that sacred, unchanging speed, it's not because it's in a race. It's because it can't go any faster. It's the fastest anything can go, not just in this galaxy or this solar system, but anywhere. It's not a speed like the speed of a car or a plane, which can be slowed down or accelerated with enough effort. No, the speed of light is a law of nature, like gravity pulling you softly back toward the bed, like time moving forward, even when we wish it would pause. It's a built-in rhythm to the fabric of reality. And yet, for something so fast, light is curiously gentle. It doesn't shout, it doesn't shove, it simply moves. Whether it's bouncing off leaves in the forest or drifting through the cold loneliness between stars, it's always there, always constant. Sometimes it's visible, golden, blue, pink at the edge of clouds. Other times, it slips out of our range entirely, into radio waves, into ultraviolet, into things our eyes were never built to catch. But it's all light, a spectrum, not a sliver, a whole ocean, not just the crest of a wave. We often take it for granted. We walk through rooms filled with it. We stare into glowing screens, never wondering about the flickers behind the images. But every time you see, light is performing a small miracle. Your eyes, those careful receptors, don't collect objects. They collect light, reflected, scattered, bent, but always arriving, always at the same speed. The shape of your room, the color of your cat, the way the candle flickers on the wall, none of these things exist in your perception without light. It paints the world into being. There's something beautiful, too, about how democratic light is. It doesn't care how big or small the object is, whether it's glancing off a dust mote or reflecting off Saturn's rings. Light treats every path as sacred. If you hold a mirror to the sun, the photons bouncing into your eye took just over 8 minutes to get here, traveling across the solar system without ever stopping, without once slowing down. No hesitation, no fatigue, just a ceaseless, wordless journey. It wasn't always clear to us what light was. Long ago, we thought it traveled instantly. You lit a torch and the cave lit up, so surely the light must have filled the space in an instant. It took centuries for us to question that intuition. The first to wonder if it moved at a finite speed did so without instruments, just with lanterns and hilltops and hopeful hearts. They tried to measure it with their eyes, their pulses, their guesses. And always, the answer seemed just out of reach, like a note you can hum but never quite sing. Then one day, a Danish astronomer watched the moons of Jupiter and noticed something odd. The timing of their eclipses changed depending on whether Earth was moving toward or away from Jupiter. It was subtle but undeniable. The only explanation? The light from those moons took time to arrive. Not much, but enough to measure, enough to prove that light didn't jump. It traveled, so it was fast, yes, but not infinite. And in that discovery, something shifted. The universe, it seemed, had a pace, a beat, a constant hum underneath everything. Even now, knowing all that, it's strange to think about how light moves through the vacuum of space. There is no sound out there, no air to carry voices or song. But light does not need air. It needs only the trembling of fields, the invisible motion of nothingness becoming something. It's quiet, yes, but full, a silence that shines. And while we sleep, light continues. Stars we cannot name still shed it. Galaxies we'll never reach still cast it across the cosmos. Every night, the sky is crowded not with what's there, but what once was. Light still arriving from events long gone. And yet, it's personal too. The same physics that governs distant quasars is what lets you see your reflection in a spoon. It's the same speed, the same light, no different, no slower. Light connects everything, from the vast to the minute, from the explosion of a dying star to the shimmer on a raindrop resting on your windowsill. It touches everything and makes no sound doing so. It's the quietest storyteller and the most loyal one. Sometimes, when all else fades, when the noise of the world softens and the day grows slow, you might catch it in its gentlest form. That last amber ray before the sun dips out of sight, the faint sheen on your wall in the evening. It doesn't clamor for attention. It just keeps arriving, unchanged, unhurried. Its message is never about urgency. It's about endurance, about movement without rest, about reaching without needing to touch. Light doesn't care if we understand it, but understanding light changes us. It invites us to think in scales and speeds we cannot feel but somehow can imagine. It asks us to believe, that even in the deepest dark, something is still moving, that even in silence, something is speaking, that even in stillness, the universe is still alive, still glowing, still passing messages across the deep. If you could ride that photon just for a moment, you wouldn't feel the wind against your face. You wouldn't feel time pass at all. You'd simply exist in motion, timeless, massless, present at every point in your journey, arriving before you left. But here in our slower worlds, we only watch it go, and that's enough. Watching is part of the listening, and light, even at its fastest, has the patience to wait. If you could slow light down, not just in your imagination, but truly slow it, you'd begin to see just how elegantly it weaves through the fabric of the world, not with haste, but with harmony. When it passes through water or glass, it bends, not because it's confused, not because it's uncertain, but because it's listening. The atoms in these materials tug on the path of light, asking it to pause just briefly as it moves through their domain. And light, though it cannot stop, does something remarkable. It detours, it shifts, it changes its course ever so slightly, as if it were leaning into a conversation with the material world. This bending, this refraction, isn't just science, it's story. It's why a straw looks broken in a glass of water, why a diamond glows with such startling brilliance, why rainbows stretch quietly across stormy skies, light being split not by force, but by patience. Each color, a different note, separated by the thickness of wavelengths, peeled apart like layers of a dream. Light travels fastest when nothing gets in its way. In the vacuum of space, it is free, unbound by molecules, untouched by mass. But introduce something, anything, between it and the emptiness, and light begins to slow. Not in speed, not truly. The photon between one atom and another still moves at that sacred pace, but the journey becomes interrupted, like a song drifting through a forest, echoed and absorbed by each tree along the way. It is not stopped, but it is asked to wait. And so, in glass it slows, in water it slows more, in diamond it moves even more cautiously, refracted again and again, until it tumbles out into our eyes in brilliant shards of spectral light. This delay, this reluctance, is what makes beauty. Without it, windows wouldn't sparkle, eyes wouldn't glisten. Light must encounter resistance to reveal itself fully. Like stories, it finds shape only when it brushes against something. Yet even when slowed, it never forgets its nature. Between each interaction, it resumes its full speed, like a messenger jogging from door to door, never late, never resting, never changing. It's not like anything else in the universe. We slow down when we get tired. We stop when we reach obstacles. But light always continues. This is one of the strangest truths about photons, these tiny quanta of light. They do not experience time. To them, there is no before and after, no journey, no delay. From their point of view, they are created and absorbed in the same instant, even if, from our view, they've traveled across galaxies. It's as if they are notes played on a piano that we hear as melody, but that exist all at once in the composer's mind. A single act, a single arc. To understand why light moves the way it does and why it cannot move faster, we have to slow ourselves down too, because the truth isn't loud. It doesn't shout from the mountaintop. It whispers in patterns and equations and pulses of possibility. Light isn't just fast, it's the fastest, and not by choice, but by design. Because here's something marvelous: light doesn't have mass, it doesn't weigh anything, not in the usual sense. That's why it moves the way it does. Things with mass can be pushed and pulled, accelerated and stopped, but light is immune. It can't be at rest. It has no setting for pause. The moment it exists, it must go, and it must go at one speed only. That number, 299 of 792 458 meters per second, isn't just a measurement. It's a limit. The speed of light, isn't just how fast light moves. It's how fast anything can move. Information, energy, matter, none of them can travel faster. It's a ceiling, not just for light, but for the universe. But that raises a question, doesn't it? Why should there be a speed limit at all? Why would the universe care how quickly something moves? To answer that, we need to look not at light, but at what it's moving through. Not space, not time, but something stranger, something softer. We call it space-time, and it's not just the background, the canvas. It's part of the picture. Space and time aren't separate. They're one thing, one continuous, flexible, interconnected whole, and the speed of light is how we translate one into the other. It's how we know how far something is based on how long light takes to reach us. It's how we measure time, not in clocks or calendars, but in light's own rhythm. Even the very definition of a meter, the length that governs every ruler, every blueprint, every plan, it's based on how far light travels in a fraction of a second. We don't measure light anymore. We use it to measure everything else. And in that quiet realization lies a deeper one. The universe doesn't use light's speed as a suggestion. It builds everything on it. Causality, that comforting rule that says things happen in order, that causes precede effects, that you can't be late for an event that hasn't happened yet, that all depends on light moving the way it does. If something could travel faster, it could arrive before it was sent. Effects could ripple backwards, unwinding time, unraveling order. The tapestry of moments would tear, and so the universe enforces a gentle boundary. It does not allow chaos to cross it, but not everything is as it seems. Some things can get close to that speed, very close. Subatomic particles in vast accelerators, whipped around in magnetic rings, racing at 99.99% of the speed of light. As they speed up, strange things begin to happen. Time, from their point of view, slows down. Distances shorten, mass increases, not in a visible way, not like swelling or stretching, but in math, in reality. The faster they move, the harder it becomes to move them faster still. The closer they get to light speed, the more the universe resists. It's as if the cosmos itself says, "This far, but no farther." We don't feel this in our daily lives. We move slowly by comparison. Even the fastest plane, the swiftest bullet, the quickest signal, none of them even reach 1,000th of light's speed. But the effects are there, hidden, like gentle eddies in a river. GPS satellites, high above the Earth, tick at different rates than clocks on the ground, all because of their speed and altitude. Engineers must account for time dilation to keep your phone's map from sending you to the wrong street. Without Einstein's insights, your directions would drift kilometers off with each passing hour, all because of light. And this is just the beginning. Light's constancy reshapes everything: how we see, how we measure, how we understand. Its speed isn't a number, it's a bridge between what we know and what we might yet learn. between our place in the world and the whisper of stars too far to touch. It is the one thing that connects all observers, no matter how fast they move, no matter where they are. Light greets them all the same, no judgment, no exception. Just a soft flicker of fairness in an otherwise asymmetric world. So next time you light a match, or switch on a lamp, or wake to a crack of dawn filtering through the trees, remember, what you're seeing isn't just brightness, it's a covenant, a rule etched into the cosmos, a whisper traveling at the only speed it's allowed to know, not because it wants to, but because it must. And as it moves through galaxies, through glass, through the back of your eye, it tells the same story over and over. That speed isn't just how fast something goes, it's how long something takes to become real. If time had a texture, a shape you could run your fingers across, it would feel like a wave riding on the back of light. Smooth in some places, stretched in others, gently folded where space begins to curve. It would whisper that nothing in this universe happens in isolation. No movement without a clock, no clock without a traveler, and no traveler without a story told in the language of motion and delay. And at the center of that story is always light. In the ordinary world, some time feels stable. You wake, you work, you rest. Seconds pass in predictable drips. But when you begin to move fast, really fast, nearing the speed of light, those seconds become elastic. Time begins to slow, not in your mind, not in your experience, but in comparison. You age more slowly. Your heartbeat ticks to a different metronome. You become unhurried while the universe flows past at double pace. This isn't metaphor. It's measured. It's real. Einstein saw it clearly before the rest of us did. While working in a quiet patent office, reviewing inventions, he was imagining what it would feel like to ride alongside a beam of light. Not to watch it from afar, but to become its companion, to match its speed stride for stride. What he found there wasn't just science, it was a new rhythm of reality, where motion and time danced in ways we had never expected. Special relativity was the name he gave to this insight, but its soul was something gentler, the idea that the laws of physics, including the speed of light, are the same for everyone, everywhere, no matter how fast they are moving. And from that quiet premise came a cascade of revelations: time dilation, length contraction, simultaneity as something relative, not absolute. If you and I witness the same two flashes of light from different places or speeds, we may not agree on which came first. In this new universe, time itself became personal. Consider two identical twins. One stays on Earth. The other boards a spaceship and travels near the speed of light. When the traveling twin returns, they are younger, not in spirit, not in attitude, but literally. Their body has experienced less time. Their cells have divided fewer times. Their memories are shorter. They have not skipped anything. They have simply lived a slower rhythm while moving fast. The spaceship didn't warp. The universe didn't break. It simply followed the rules it always has, rules written in the light. And this isn't just a thought experiment. We've flown atomic clocks around the Earth on planes, compared them with stationary ones, and found that the airborne clocks tick more slowly. We've seen this effect in the decay of particles moving near light speed, decay delayed, as if time itself was hesitant to touch them. The universe isn't metaphorically strange, it's literally, elegantly strange. But speed alone doesn't bend time. Gravity does too. Imagine space and time not as separate ideas, but as a single woven cloth. When mass is placed upon it, a planet, a star, your own body, it dents the fabric ever so slightly. Light, which always travels in the straightest line possible, must follow that curved path. It's not being pulled, it's not being pushed. It's simply following the rule. Move at light speed along the shortest possible route. But the shortest route now curves. This bending of space-time is gravity, not as a force, but as a whisper in the geometry of the cosmos. Earth tells the sun how to move, not with a tug, but by shaping the space around it. The sun does the same for Earth, and light, moving through these curved regions, bends too. We've seen starlight curve around massive galaxies, a phenomenon called gravitational lensing. Sometimes, this bending creates arcs and rings of light around invisible things, revealing mass where no stars exist. In these distortions, we glimpse the unseen, black holes, dark matter, galaxies long vanished. And time slows in these curves too. The closer you are to something massive, the slower your clock ticks. Stand at the bottom of a mountain, and your seconds are just a little bit longer than someone at the top. Atomic clocks have proven it. Even the few centimeters between your head and your feet hold a difference, minuscule but real. Your head ages faster than your toes. The GPS satellites we rely on wouldn't work without correcting for both special and general relativity. The satellites move fast, so their clocks tick slower, but they're also farther from Earth's gravity, so their clocks tick faster. These competing effects must be balanced so that when your phone asks the sky where you are, it doesn't get confused. And all of this, every calculation, every adjustment, returns to that constant, that unwavering drumbeat, the speed of light. It's as if the universe wrote itself to this rhythm, and yet it did so without metronomes or tuning forks. It used the dance of fields and particles, the geometry of nothingness, and a quiet rule. The light shall always travel at the same speed, no matter who watches, no matter how fast they go. But what happens when we push against that limit, when we try to move something, anything, faster than light? Here's the dilemma. As you push an object faster and faster, it doesn't just gain speed, it gains energy, and not in a simple, linear way. The closer you get to light speed, the more energy you must pour in. The curve rises steeply, exponentially, until just before light speed, the required energy becomes infinite, not metaphorically, not hypothetically, truly infinite. And infinite energy doesn't exist, not in any corner of the cosmos. So nothing with mass can ever reach that speed. It's not about technology. It's not about ambition. It's about permission. The universe simply won't allow it. That's why photons, those tiny massless packets of light, are the only things that can move at that ultimate pace. They are not just the fastest things. They are the only things allowed to be that fast. Everything else must follow behind. They're the first responders in a dark universe, the earliest arrivals to every event. When a star explodes, it is light that tells the story first. When you strike a match, it is light that announces the fire. When a distant planet reflects its parent star, it is light that carries its soft glimmer to your eye across time and silence. And still, despite all we know, light holds secrets. It behaves as both wave and particle, but never both at once. When we don't look, it travels as a wave, spreading out, interfering with itself, painting probabilities across empty space. But the moment we observe it, it chooses. It lands as a particle. It arrives, it collapses, it becomes known. Why? No one quite knows. But it's as though light waits to be witnessed before becoming real. And so we build machines to chase it. We build telescopes that drink starlight and microscopes that scatter it. We use it to send messages, to burn information into plastic discs, to carve paths through tissue and steel. We even use it to trap atoms in delicate lattices of focused beams. Light, once mysterious, now becomes a tool, a scalpel, a cradle. And yet, despite all this mastery, we cannot change its speed. That remains untouched, sacred. If one day we meet someone or something beyond our planet, we'll know them first through light, through the wobble of a star, the dimming of its glow, the fingerprint of elements burned into spectra. Long before we shake hands, we will see their sunrises. We will know their chemical histories, all because of the story light carries, all because it cannot be hurried, cannot be altered, cannot lie. Every time we stare into the night sky, we're not seeing stars as they are, but as they were. Some may already be gone, their light still traveling through space, still on its way to us, still telling a story that ended long ago. The night is a museum of moments, and light is the archivist. And perhaps that is the most beautiful part, that in light's inability to move faster, we are granted a glimpse into the past. The speed of light does not restrict us. It reveals to us a universe in motion, not in snapshots, but in echoes, not in presence, but in memory. It allows time to be felt across distance. It allows us to see what was, and in that to wonder what will be. If you could press your ear gently against the fabric of the universe and listen, not to the clamor of stars or the whisper of planets turning, but to the silence between, it would be the sound of light arriving, always arriving, not early, not late, just in time to trace the edges of what has been. And in that soft arrival lies the most delicate truth of all, that the speed of light is not simply how fast something moves. It is how the universe connects one moment to the next. This connection is not just between stars and galaxies. It exists between thoughts, between signals, between cause and effect. Every flick of a light switch, every echo of a voice bouncing off a wall, every beam that reflects off the surface of your eye, it all obeys the same limit, this far and no farther. And within that limit, an entire symphony unfolds. Because when the tempo is fixed, the music becomes everything. There's a beautiful tool that physicists use to describe how events are allowed to influence each other. It's called a light cone. Not a cone you can hold or touch, but a conceptual shape. Imagine a single point in space-time, the striking of a match, the falling of a leaf. From that point, light moves outward in all directions, forming an expanding sphere. If you draw it in a diagram, with time rising like the trunk of a tree and space spreading out like the branches, the path of light makes a cone. Everything inside that cone can be touched by what just happened. Everything's outside of it is out of reach, unreachable because light hasn't gotten there yet. This cone doesn't just describe where light can go, it describes where influence can go. If something lies outside your light cone, you can't touch it, you can't change it, you can't even know it exists until light arrives. It's as if the universe draws soft borders around every moment, saying, within here you may act, beyond saw you must wait. It means that no signal can travel faster than light, no whisper across space, no alarm through time. That delay, the time it takes for light to cross a distance, isn't a flaw, it's a feature. It gives the universe order. Without it, chaos would flood in. You could see effects before their causes. You could send messages into your past. You could watch yourself press a button before your finger even moved. But with light's limit, the world makes sense. You press the button. A moment later, the light turns on, not because it couldn't turn on faster, but because the rules say it must wait for the message to arrive. That moment, the small, imperceptible delay between intention and reaction, is the heartbeat of the universe. Even our daily technology is laced with these invisible delays. When you stream a movie, when you call a friend across the globe, the signals race as fast as they can through cables, satellites, fiber optics. But they are still bounded by light's limit. If your friend is on the other side of the planet, your words take a fraction of a second to get there. Tiny, yes, but real. And if your friend were on Mars, that delay would stretch to minutes. A conversation slowed to the rhythm of the cosmos. There's a strange poetry in that no matter how far we stretch our arms, no matter how much we try to erase distance, the universe reminds us, patience. Every connection is a journey. Every response must travel, and every moment must wait its turn. But this delay is also what lets us look backward. Because light moves at a finite speed, we are always seeing the past. When you gaze at the moon, you are seeing it as it was about 1.25 seconds ago. The sun, 8 minutes. The nearest star beyond that, more than 4 years. And galaxies, millions, billions. The night sky is not a map, it is a memory, a portrait of what once was, painted in photons. Some of the stars you see may no longer exist. Their light, like a postcard sent long ago, is only now arriving. This is not sad, it's intimate. You are receiving the last words of distant giants, whispered across time and space, preserved in their journey. Astronomers live in this past. Their telescopes are not just instruments, they are time machines. With each increase in sensitivity, in resolution, they peel back the layers of the cosmos, not deeper into space, but deeper into history. They can see galaxies as they were when the universe was young, newborn, full of possibilities. They study light that left its source before our planet even formed. And this light doesn't just carry images, it carries fingerprints. It encodes temperature, composition, motion. In the shift of a spectral line, we learn how fast something is moving away. In the flicker of a distant quasar, we glimpse the rhythm of a black hole feeding in darkness. In the dimming of a nearby star, we detect the transit of a planet that might, just might, harbor life. All of this because light cannot go faster. You might wonder why we can't speed it up. After all, we've sped up so much. We've broken the sound barrier, sent probes beyond the edge of our solar system, accelerated particles to near light velocities. Surely light itself could be surpassed. But light is not a train to be outrun. It is the track, the measure by which speed itself is defined. To move faster than light would be to undo the very meaning of distance and time. The equations that hold the universe together would unravel. Causality, the sacred order of things, would be torn apart. That's not just a theoretical danger. It's a logical impossibility. But that hasn't stopped us from imagining. Science fiction is full of warp drives, hyperspace, wormholes, and some of those ideas, strange and speculative as they are, have a sliver of grounding in physics. They don't propose moving faster than light in the usual sense. Instead, they imagine bending spacetime, folding it, so the path between 2 points becomes shorter. The traveler isn't speeding up. The universe is shifting around them. Still, such feats would require energies and materials we have never observed. Exotic matter with negative mass, fields that curve space without crushing it. For now, they remain dreams, soft ideas we keep in the drawer with star maps and lullabies. And perhaps that's where they belong, because there is something quietly comforting about a speed that cannot be exceeded. It gives the universe structure. It gives us perspective. It gives us the delay that makes wonder possible. Imagine if you could see everything instantly. No distance, no waiting. The stars would all arrive at once, blinding and flattened. The past would collapse into the present. There would be no unfolding, no mystery, no progression. It is the delay, the finite, gentle pace of light that allows awe to bloom. That lets a sunrise feel gradual, a memory feel distant, a moment feel earned. And so we accept it, not as a barrier, but as a blessing. The speed of light is not a wall we crash against. It is the pace at which the story is told. Any faster, and we would lose the plot. Every time a star pulses in the sky, every time a firefly blinks in the dark, every time a lighthouse spins its lonely beam across the sea, it is obeying this quiet law. No matter how bright, how desperate, how far, it must travel at that pace, the same pace, for everyone, everywhere, forever. And if you sit very still in the hush between thoughts, you might feel it too, not the motion, but the patience, the quiet, perfect patience of something that has always moved the same way from the beginning of time to now, a steady glimmer, a traveling truth, a light that always arrives exactly when it should. Somewhere in a patch of sky so quiet it hums, a single photon begins its journey. It slips away from the searing heart of a star, bursting through layers of plasma, threading past magnetic fields, emerging into the deep and empty dark. No engine drives it. No one steers. It simply moves as it must, at the speed written into the bones of reality. It doesn't look back. It doesn't wonder where it's going. But it goes. Across decades, across centuries, across space so vast and still, we have to fold it in our minds just to picture it. And then, without a sound, it arrives. At the curve of a lens, at the surface of an eye, in the corner of a telescope, waiting in silence. That journey, so impossibly fast and impossibly long, is what lets us see. Not just see light, but see the universe. Everything you know by sight is a story told by photons. They touch nothing, they weigh nothing, but they bring you everything. And yet, we might ask, why this speed? Why not faster? Why not infinite? If light is made of no mass, why does it not simply leap across space instantaneously? The answer lies deep in the structure of the universe, not in what it's made of, but in how it behaves. There's a quiet set of equations, elegant and unassuming, known as Maxwell's equations. They describe how electric and magnetic fields dance, how they change and influence one another. Alone, each field might ripple, but together they create something new, a self-sustaining wave, a disturbance that feeds itself as it moves, a pulse of energy that travels not because it's pushed, but because it cannot help but move. And when you solve those equations, when you trace the shape of those fields, the result tumbles out like a whisper, a speed, not any speed, but the speed, the very number we've been carrying through these dreams, not chosen, not assigned, but inevitable, a product of the electric and magnetic constants of the vacuum, a built in feature of space itself. That's why light moves the way it does, not because someone decided it should, but because it must, because the universe made it so in the very rules it wrote to govern its fields. And once that speed exists, it becomes the ultimate reference. Everything else measures against it. Time bends around it. Space contracts before it. It is the axis on which causality spins. But light's speed isn't just about electromagnetism. It is deeply tied to the very shape of spacetime. In Einstein's theory of relativity, the speed of light becomes more than a number. It becomes the speed at which the universe trades space for time. Move faster through space, and time slows down for you. Try to catch light, and time for you nearly stops. Push harder, and you reach a wall, not a barrier in front of you, but a soft wall in your equations, where energy required becomes infinite, where mass stretches to infinity, and where time dissolves. It's like chasing the edge of a dream. The faster you go, the more the dream slips ahead, never changing pace, never waiting. And in that chase, the universe shifts around you. Your rulers shrink, your clocks slow, the distance shortens. And yet, no matter how close you come, light remains just beyond reach. This is no coincidence. It's not even a limit in the way we usually understand limits. It's more like a defining line between what can exist and what cannot. Everything with mass is tethered below that line, and only light and massless companions like gravitational waves live on it. They don't traverse the universe like runners. They are the fabric itself, woven into every field and fluctuation. So when we speak of light's speed, we're really speaking about something much larger, about how time unfolds, about how information is allowed to spread, about how the story of the cosmos gets told from one atom to another, because even information has a speed limit. You cannot know about something until light or a signal traveling at light speed reaches you. There's no cheating this, no instant awareness, no universal now. The present, as strange as it sounds, is local. The stars above you are not experiencing the same moment as your thoughts. Even your reflection in a mirror is a sliver of the past, a fragment delayed by mere nanoseconds, but delayed nonetheless. This is not a flaw. It is a gift. A world without delay would be a world without sequence, without before and after, without stories. The lag between action and reaction, between event and awareness, gives meaning to time. The silence before the thunder, the light before the sound, the slow unraveling of sunrise across a sleeping hill. Even in the heart of our technology, this limit persists. Lasers in communication satellites, fiber optic strands beneath oceans, computer chips blinking in binary. They all send their messages at the speed of light and not one bit faster. Every signal you receive, every image you see, every video you stream is just light being harnessed, bent, guided through channels and mirrors and air. And even when we think we've outsmarted it, when we split electrons in quantum entanglement, when we observe particles echo each other across space, the truth remains. No usable information travels faster than light. The universe permits coincidence, but not cheating. Still, the imagination wanders. Could there be something else, something unknown that moves faster? Could there be a deeper speed, a hidden layer? Theoretical physics plays with ideas, tachyons, hypothetical particles that always travel faster than light, but can never slow down. They remain purely imaginary. Not one has ever been observed, not even a hint. Then there are thought experiments. What if we could bend space itself? Shorten the path rather than quicken the pace? A warp drive like folding a piece of paper and punching through. The math isn't forbidden, but the requirements are strange. Negative energy, exotic matter, energy equivalent to a planet compressed into a handful of space. It's not ruled out entirely, but it lies beyond our reach, like a mirage on the horizon of what's possible, and perhaps that's where it belongs. Because a universe where light is the fastest thing is a universe we can understand, predict, navigate, trust. The constancy of its speed means that wherever we go, whatever we see, we are anchored by something that never changes. We are always looking back, yes, but in doing so, we are always seeing something real. Even in darkness, light is present, absorbed, scattered, hidden in the warmth of objects, waiting in the glow of a star behind a cloud. And where it moves, it brings not just vision, but structure. It tells particles where to go. It builds atoms. It writes the very recipe of color, of chemistry, of sight and sensation. You could say, without light, there is no meaning. And without its speed, there is no order. The speed of light, then, is not just a maximum. It's a memory, a message, a map. Every beam you see is a record of where it's been and how long it took to get here. It carries not just brightness, but chronology. It's what makes the past visible, the present comprehensible, and the future predictable. So the next time you stand in sunlight, or watch headlights gliding across a wet road, or trace the ghostly outline of a moon haloed by mist, remember that what you're witnessing is not just an effect, it's a boundary, a gentle but unbreakable rule, and within that rule, everything unfolds with perfect grace. It's not that light can't go faster, it's that if it did, the entire world would come undone. The ripple would move ahead of the stone. The answer would arrive before the question, and the stars would flash and vanish all at once. Instead, they shimmer. They take their time. They travel as fast as nature allows. And in doing so, they teach us patience. If you close your eyes and imagine the universe breathing, not in gasps or bellows, but in a soft rhythm, an exhale of stars, an inhale of silence, you might begin to feel how everything pulses in time with light, not in its brightness, but in its timing, in the way it connects not just space to space, but moment to moment, like threads drawn through beads on a string. And at the center of that thread lies a question so old it hums. What makes time move forward? The answer, like a candle's glow, is both simple and mysterious. Time moves forward because light such moves forward, not with preference, not with urgency, but with constancy. The speed of light sets a direction, not in space, but in causality. It is the reason why causes always lead and effects always follow, why memories trail behind and possibilities wait ahead. If there were no limit, if signals could race backward, the entire structure would dissolve. The puzzle would lose its frame. Every signal you send into the world, every glance, every word, every heartbeat captured on a monitor, is carried by some form of light, not always visible, but always electromagnetic. And each of those signals obeys the same commandment: do not exceed the speed that binds the cosmos. You may stretch, you may shift, but you may not surpass. The universe is not punishing us with this limit, it's guiding us, the way a river guides a leaf, the way a breeze arranges petals on the ground. And yet, despite this profound restraint, light is full of wonder, full of play. When it enters a prism, it bends, each color curving at a slightly different angle, revealing the spectrum hidden inside what once looked white. Red drifts gently, violet turns sharply, and in that slow cascade of color, we glimpse the richness of a speed that doesn't waver but always responds. Different wavelengths, different energies, all traveling at the same speed in vacuum, yet reacting uniquely to the world they pass through. This interaction is what lets us see more than just brightness. It gives us color. A red apple is not red because it holds redness inside. It is red because it absorbs every other color and reflects red back to your eyes. Your mind translates that reflection into meaning. The sky is blue, not because air is blue, but because short wavelengths scatter more in the atmosphere, bouncing around until blue light reaches us from every direction. The setting sun turns gold and crimson as those shorter waves get scattered away, leaving behind the longer, richer reds. None of this happens if light doesn't interact. If it simply passed through everything untouched, we would live in a world without shape, without contrast. It is light's patience, its willingness to slow down, to bend, to scatter, that gives the world its texture, its edges, its soul. And still, even as it dances and delays, light in a vacuum never changes pace. Whether it left a star 5 seconds ago or 5 billion years ago, it glides through the emptiness at the same immutable speed. This makes light a messenger of unparalleled precision. It brings not just images, but timing. Astronomers measure the flicker of pulsars, dead stars spinning with exacting rhythm, by the light they emit. Entire galaxies announce their movements through Doppler shifts, the stretching or compression of their light as they move away or toward us. From these tiny shifts, we know the universe is expanding, that galaxies are drifting apart, that space itself is stretching like dough, and in that stretch, something strange happens. Light, too, is stretched. Its wavelength lengthens. Its color shifts toward red. This is the redshift, a slow unraveling of energy over time, not because light slows, but because the space it crosses grows larger beneath it. The light from the earliest galaxies has been so redshifted that it now arrives not as visible light, but as microwaves, soft, gentle whispers from a time when the universe was still a child. This light fills the sky in all directions. It is the cosmic microwave background, the echo of the Big Bang, a glow not of stars, but of existence itself coming into being. And we can still see it, bathe in it, measure it, because it moves always at that same steady pace. Even here, light is not just illumination, it is evidence of time, of distance, of origin. And what of massless companions, those that share light's speed but wear different names? Gravitational waves, for instance, ripples in spacetime itself, also travel at the speed of light. They are born in violence, black holes colliding, neutron stars crashing, but they spread outward gently, like circles on a pond too vast to see. And now, with delicate detectors on Earth, we can listen to them, not with ears, but with lasers. We watch how space stretches and contracts in response. And always, those waves travel no faster than light, not because they are light, but because they too obey the same cosmic rhythm. Even when the universe screams, it does so with restraint. It is tempting to wonder, in the deep quiet, if this speed limit is not a wall, but a doorway. Perhaps it doesn't prevent us from traveling fast. It simply reminds us that information, that presence, that reality itself must unfold in order. You cannot arrive before you begin. You cannot see without being seen. This unfolding, so gentle and so firm, is what gives us cause and effect, night and day, yesterday and tomorrow. So when we say nothing can go faster than light, we are not saying the universe is closed. We are saying it is consistent, predictable, elegant. And that is what makes science possible. That is what lets us build, calculate, send rovers to Mars, bounce lasers off the moon, scan galaxies from mountaintops and radio dishes. Because light always moves the same way, we can map the chaos. We can write poetry in equations. Even in the smallest distances, the tiniest delays matter. In particle accelerators, researchers track photons to fractions of nanoseconds. In your phone, your GPS depends on signals arriving exactly when expected, no sooner, no later. Atomic clocks use the vibration of atoms, driven by microwaves, a cousin of light, to count time with staggering accuracy. These clocks are so precise that they would not lose a second in millions of years, all built on the same truth, the constancy of light's pace. And still, light finds new ways to surprise us. In materials known as metamaterials, scientists have managed to slow light dramatically, not by breaking the rule, but by weaving spaces so complex that photons take longer, like a traveler caught in winding alleyways. In labs, light has been slowed to walking speed, paused entirely within clouds of cold atoms. But between those atoms, it still races. The rule still holds. The pause is not a break, it is a breath. Even the idea of darkness is not an absence of light, but a waiting, a place light has not yet reached or has already passed. When you stand in shadow, you are simply on the wrong side of the moment, and when light returns, it brings not just vision, but warmth. It lets the world resume. So much of what we feel, what we understand, is carried by light. Not just sight, but time. Not just warmth, but order. It is in the reflection of your face in a window at night. It is in the shimmer of oil on water, in the glint of dew on grass before dawn. It is the last thing you see before you sleep, and the first hint of morning when your dreams begin to fade. And it never hurries, not once, not ever. Even in its brilliance, light is bound. Even in its freedom, it is defined. And in that paradox lies its magic. Imagine looking up at the night sky, not just as a casual observer, but as someone quietly aware that every pinprick of light above you is not where it seems. Those stars, flickering gently through layers of air and time, are not shining in this moment. Their glow left them long ago. What you see is not their present, it is their past, sailing toward you on the back of light, traveling faithfully across the silence of space. The stars are still sending their messages, and you, lying there under blankets or beside a window, are their final stop. Every glance skyward is a journey backward in time. The further you look, the deeper into history you peer. Light becomes a courier, carrying not just brightness, but the evidence. Each beam has traveled thousands, millions, sometimes billions of years just to fall softly into your eyes. A star you admire tonight may no longer even exist. Its furnace may have already gone out, collapsed, or burst into supernova, but its light, unknowing and undeterred, still arrives. This is how light makes memory visible, and the deeper we look, the older the light becomes. Our most powerful telescopes peer so far that they see not galaxies as they are, but galaxies as they were when the universe itself was young. These observations aren't like snapshots in an album, they're more like fossils still glowing, ancient signals that have traveled through expanding space, stretched, dimmed, but never erased. The further away an object is, the longer its light has taken to reach us. But something stranger happens as that distance increases. Space itself is expanding, not like an explosion, but like dough rising quietly, stretching the fabric between everything. As light moves through this stretching space, its wavelength elongates, its color shifts toward red. What began as ultraviolet may arrive as infrared. What began as visible light may end its journey as a whisper of microwaves. This is cosmic redshift, and it doesn't mean the light is tired. It means the universe is growing. The light hasn't slowed down. It still travels at the same perfect speed, but the space beneath it has expanded, like a road lengthening while the car drives. And so the journey becomes longer, not because of any resistance, but because of the nature of space itself. This stretching has a rhythm, a pace we can measure. It tells us the universe is not static, but in motion. It tells us everything is drifting, galaxies sliding away from one another like boats on a dark sea. It was Edwin Hubble who first noticed this, who saw that the further away a galaxy was, the faster it seemed to be receding. The light from those galaxies was stretched, redshifted, as if echoing the motion itself. From this came the idea of the expanding universe, and from that, the Big Bang. Not an explosion in space, but the expansion of space itself. Not a fireball from a center, but the quiet, even blooming of everything, everywhere, all at once. The light we observe today from the farthest reaches comes not just from distant stars, but from the very fabric of the cosmos beginning to glow. This is the cosmic microwave background, the afterglow of creation, still arriving, still washing over us, still carrying the imprint of the first light. It is everywhere, in every direction. It's not visible to your eyes, but it is there, faint and uniform, a background whisper that fills the sky. It's the oldest light we can see. It has been traveling for nearly 14 billion years. And even now, after so long, it moves at the same unchanging speed, the same universal rhythm. So when we speak of light as a limit, we must also speak of it as a gift. Without that speed, without that finite measured delay, none of this would be visible. The stars would overwhelm us with their immediacy. The past would collapse into the now, and we would lose the ability to see our place in the story. It is light's pace, its refusal to rush, that makes the universe readable. Every glimmer tells you how far it has come. Every shade tells you how long it has traveled. And together, those beams form a kind of clockwork, not ticking forward, but stretching backward, measuring not time ahead, but time behind. Even our own sun is not present in real time. Its light takes just over 8 minutes to reach us. When you feel its warmth, see its rays, you're sensing a version of the sun that no longer exists. Not in a dramatic way, just 8 minutes old, but enough to remind us that nothing is instant, not even light, especially not light. And that delay gives us something remarkable. It gives us perspective, not metaphorically, but literally. Light allows us to see things not only as they are, but as they were, to map motion, to trace age, to understand evolution, not just of stars and galaxies, but of the very structure of space. Astronomers now measure the light from exploding stars in distant galaxies, supernova, and use them to calculate the rate of cosmic expansion. They've discovered that this expansion is accelerating, driven by something we barely understand: dark energy, an invisible pressure pushing the universe apart faster and faster. And how did we find it? Not with particles, not with gravity, but with light, with its timing, with its soft, unyielding rhythm. And so we come to understand the cosmos, not by touching it, but by receiving its light. We don't fly to stars, we don't visit other galaxies, but we listen. We gather the photons, we measure their arrival, and we build a picture not of where we are, but of when we are. That picture is always in motion. Every night, new light arrives, ancient light, fresh to us, but old in its own way. It becomes part of our story. Our telescopes collect it, our sensors record it, our minds weave it into meaning. The universe doesn't knock, it doesn't announce itself. It simply glows and waits for us to see. And when we do see, we see in layers. The moon's light delayed by a second, the sun's by minutes, the stars by years, the galaxies by millennia. It's a stacked timeline, a slow, layered diary of light, with every page written in the same hand, every sentence delivered at the same pace. Even light that is absorbed by clouds, by dust, by the dark gas between galaxies, still follows the rule. It doesn't try to arrive early. It simply fades, dims, becomes background, but never breaks the speed. And even as we imagine futures where we build greater observatories, where we collect more ancient photons, where we stretch the limits of visibility to the edge of time itself, we know the constraint will still hold. We will not see further by traveling faster. We will only see more by waiting longer, by reaching deeper, by listening more closely. That's the paradox, isn't it? That the fastest thing in the universe is also what teaches us to be patient. That the speed of light, unchanging and firm, becomes a meditation, a lullaby from the stars. It says everything will arrive, in time, in order, in rhythm. And so, each night, the sky becomes a quiet procession of arrivals, a soft unfolding, a slow pageant of past and present, painted in points of light. And we, the watchers beneath it, are not separate. We are part of it. We reflect light, too. We emit warmth, shine signals, leave traces. Our eyes, our memories, our instruments, all of them echo the same constant. All of them are touched by the same speed. And when we dream, it's often in light, not in words, not in sounds, but in glows and flickers and scenes cast gently across the mind's eye, as if our thoughts, too, travel at the speed of something unseen, as if memory is just a kind of photon echoing inside the body. There's a hush that comes just before dawn when the world seems to hold its breath. The sky is neither night nor day, but something in between, a blue that hasn't yet chosen a direction. In that moment, even your thoughts slow down, not because you are tired, but because the pace of light is already beginning to fill the sky again. It creeps softly across the horizon, not in leaps or sparks, but in gradients, The darkness fades not because it flees, but because the photons have returned one by one, quietly reclaiming the world. But if you could pause time right there, if you could freeze the very instant a single ray of sunlight touched the roof of your house or the leaf outside your window, and look deep into that moment, you'd find something even stranger hiding in the silence. Light, even now, is moving in a way we still don't fully understand. It behaves like a wave, spreading, interfering, overlapping, but also like a particle, arriving in quantized bursts, as if it were counting its own steps. This dual nature, wave and particle, has puzzled scientists for generations, and yet it is not a contradiction. It is a mystery we are invited to observe, but never fully grasp. In experiments, light sometimes behaves as though it travels in waves, rippling through slits, creating delicate patterns of interference, like raindrops falling on a pond. But in other moments, it behaves as a stream of particles, photons that seem to arrive one by one, like pebbles tossed gently into the dark. We call this duality, but the word feels too sharp, too final. It implies that light is split into two roles. What if instead it is something else entirely? Something that only resembles a wave when you ask it to, and resembles a particle when you insist, like a shape made of fog, taking the form you expect, only long enough to be recognized. This mystery deepens in the presence of the double-slit experiment, perhaps the most poetic riddle science has ever written. If you shine light through two narrow openings, it creates an interference pattern on the screen beyond, bright and dark bands like the ripples of two stones cast in still water. Even if you send one photon at a time, those bands slowly build up. The light seems to know both paths, to interfere with itself, to be, in some strange way, in more than one place at once. But here's where it gets eerie. If you try to observe which slit the photon goes through, if you set up a detector, if you ask the question too loudly, the pattern disappears. The light no longer behaves like a wave. It chooses a path, like a particle. The interference vanishes. It is as though the light changes its behavior because you looked, because you asked, because you tried to know. And so we are left with a haunting idea that reality itself may not fully exist until it is observed. That light does not settle into a shape until it is seen. This isn't just philosophy, it's quantum mechanics, a field that lives in the delicate hush between certainty and possibility. At the heart of it all is the photon, a quantum of light. It has no mass, it has no rest frame. It is born in motion and dies in arrival. It doesn't experience time. From its perspective, the moment it is emitted and the moment it is absorbed are the same. It never travels. It simply connects two events. You can't slow it down. You can't speed it up. In the vacuum of space, it always travels at the same speed. Even when you chase it, even when you flee from it, it moves away from you at the exact same pace. It doesn't care how fast you're going. It doesn't play favorites. It is the one thing in the universe that sees all motion the same. But there's more to this than just motion. There's meaning. Because photons aren't just carriers of light, they are carriers of information. When you look at anything, you are not seeing the object itself. You are seeing the photons it has sent to you. They carry data, shape, color, temperature, texture. They whisper the story of whatever they touched before arriving. They are tiny messengers, and your eyes are where their journeys end. That's why vision is never passive. You are not simply letting light fall into your eyes. You are receiving the final step of a story that began in a lamp, or a flame, or a star. And because photons travel at the ultimate speed, that story unfolds in a way that obeys the deepest laws of reality. You cannot see something before its light reaches you. You cannot know something before it arrives. And yet, entanglement, another quantum marvel, seems to hint at a kind of togetherness that is not bound by speed. When two particles become entangled, their states are linked no matter how far apart they are. Change one, and the other changes instantly. It feels faster than light. It feels like a secret shared across the universe. But information doesn't travel in that link. No message is sent. Nothing breaks the rule. It's not communication, it's correlation. And so, even here, light remains the limit. The speed of light is not just about distance, it is about order. It is about the story having a beginning, a middle, and an end. If anything could outrun light, it could rewrite that story. It could send a whisper backward through time, and suddenly the cause would trail behind its own effect. The universe would lose its narrative, and everything, memory, history, science, would come undone. That's why light is not a barrier. It's a safeguard, a keeper of time's arrow, a quiet, universal promise that the future will never arrive before the present, that moments cannot be rearranged, that life flows forward, one photon at a time. And yet, within that flow, there is so much room for play. Photons bounce and reflect, refract and scatter. They carry warmth, they carry vision. They are the reason a field of grass glows gold at sunset, why your eyes sparkle in the morning light, why the moon is anything more than a pale rock in the sky. They make the world visible, and they make it beautiful. Even in their quietest forms, they shape your life. Microwave photons cook your food, infrared ones warm your skin, ultraviolet ones tan or burn, depending on your caution. X-ray photons peer into your bones. Gamma rays whisper from deep space, telling tales of exploding stars. And radio photons, stretched out and gentle, bring you music and voices from places far away. All of them, no matter their frequency or energy, are light. All of them move at the same speed and vacuum. All of them obey the same rule. It's a kind of equality that feels sacred, a harmony that underpins all of nature. The smallest beam, the brightest flash, they follow the same path, speak the same language, heed the same law. And we, the watchers, the dreamers, the listeners beneath their journey, are the ones privileged enough to see their glow. So when you close your eyes tonight and you feel the darkness wrap gently around your shoulders, know this. The darkness is not the absence of light. It is the pause between arrivals, the moment just before a photon finds its way to you, the breath before a new flicker begins. And it will begin. It always does. Somewhere, light is on its way, unseen, unstoppable, unfolding the story of everything. There's a kind of magic that happens when light moves through water, not in theory, but in the quiet shimmering of a swimming pool at midday, or the soft blue that deepens around your feet as you wade into the sea. It bends, it slows, it dances, not because it wants to, but because it must. In these moments, you're witnessing light in conversation with matter, a dialogue of angles and energy, of subtle delays and graceful shifts. And yet, even here, light is still obeying the same law. still moving at its own immutable pace whenever it is between atoms, in the tiny vacuums that stretch invisibly between molecules. But when it travels through something, water, air, glass, it is not truly slowed like a tired traveler resting on the roadside. It's being delayed by interactions, by brief, imperceptible exchanges with the particles that make up the world around it. It is stopped and started over and over again, absorbed and re-emitted, each interruption a moment so small we cannot measure it. But add them together, and the journey takes longer. That is how light slows, not because it forgets its speed, but because it must pause to say hello. And yet, there is something even stranger, because while nothing with mass can ever reach the speed of light, it is possible, under very special conditions, for something to move faster than light does in a material. Not faster than light in a vacuum, no, that limit still holds. But faster than light through water? That's something else entirely. This happens in nuclear reactors. Deep beneath the surface, where fuel rods glow with a ghostly blue, something remarkable is happening. Electrons, flung from atomic reactions, are moving faster than the speed of light would move through the surrounding water. And just like a sonic boom, which occurs when an object breaks the speed of sound, these electrons create a kind of photonic boom, a cone of electromagnetic shock waves. This is Cherenkov radiation, a name that feels technical but hides something dreamlike. It's the glow of speed outpacing light's local pace. A luminescent halo born not from heat, but from violation, not of universal law, but of local condition. The water tries to resist. The photons ripple out in blue, the shortest visible wavelength not absorbed by the liquid's depths. It's light's way of saying, "You startled me." To see Cherenkov radiation is to glimpse a kind of echo from a boundary nearly crossed. Not the ultimate speed limit, but a regional one, briefly outpaced. And though the particles don't break the universal limit, the effect feels electric, visible proof that even light has constraints in some places, that its speed isn't always the same depending on what it moves through. In glass, light slows to about 2/3 its vacuum speed. In water, it's roughly 3/4. In diamond, slower still. But between every molecule, in a spaces too small to name, light still zips along at its native speed. That number, 299 to 792, 458 meters per second, is still honored. It is just interrupted, like a thought paused by blinking, like a melody played staccato. And this behavior gives us the phenomena we live with every day. Lenses bend light because of refraction, the change in speed causing it to change direction. Raindrops act as tiny prisms, creating rainbows by slowing and splitting light into its many frequencies. The sparkle in a gem is not from the stone itself, but from the way it bends, traps, and reflects light at just the right angles. The world shimmers not because it is bright, but because light is always adapting. And so are we. Our eyes are made for light, evolved to detect just a narrow sliver of the electromagnetic spectrum, the visible range. But that spectrum is vast. Below red, there's infrared, gentle warmth, the language of heat. Below that, microwaves and radio waves, long and low in energy, carrying signals and songs. Above violets, ultraviolet, sharp and bright, capable of tanning skin and triggering reactions. Beyond that, X-rays and gamma rays, short, intense, and powerful. All of it is light. All of it travels at the same speed in vacuum. The only difference is frequency, wavelength, and how our instruments or our bodies respond to it. To a bee, a flower glows in ultraviolet. To a snake, with the warm mouse in the shadows, is outlined in infrared. To a radio telescope, the galaxy hums in long, slow pulses. Every creature, every machine hears a different voice in the same language. And yet, no matter the tone, the voice never shouts. It whispers at light speed. We've used that whisper to build our modern world. Fiber optic cables, glass strands thinner than a hair, carry light across continents. Inside them, light bounces and reflects, traveling in curves that would make any dancer proud. That light carries data: your calls, your videos, your questions, your answers. And despite bouncing millions of times, despite being redirected and filtered and amplified, it still obeys the speed limit. It still honors the pact. In these fibers, in these tiny rivers of glass, we are sending information as pulses of light, binary flashes, on and off, presence and absence, and in those flickers, entire conversations. The world is bound by light, but it is also connected by it. Satellites orbiting Earth send laser pulses to one another, to ground stations, to ships, to aircraft. The pulses move through vacuum, mostly uninterrupted, traveling at full speed. But even here, the distance adds delay. The further the message must go, the longer it takes, not because the light slows, but because the space stretches, and those delays matter. They must be accounted for. They define how quickly a command reaches a rover on Mars, how fast a telescope relays its data, how long a GPS signal takes to tell your phone where you are. These are not just measurements, they are consequences. The world moves to the rhythm of light's pace, whether we notice it or not. Sometimes we try to trap light, not forever, but for a moment. In experiments, scientists have slowed light to walking speed, just a few meters per second, not by changing its nature, but by suspending it in a medium, manipulating the atoms around it, creating a kind of optical molasses. The photon doesn't stop, but its forward journey is delayed by detours, by side quests through quantum states. In the coldest laboratories, light has been held, paused within a cloud of ultra-cold atoms, stored as memory, as possibility, and then released again. These tricks don't violate the speed limit. They dance with it. They remind us that light's path is not always straight, and its journey is not always swift, but its essence, its identity remains. And even in the most exotic corners of the universe, in neutron stars, in supernova remnants, near the edges of black holes, light is still bound to the same rule. It bends, it stretches, it shifts in frequency, energy, color, but it never speeds up. That's not in vacuum, not even once. Black holes themselves are defined by what light cannot do. When the gravity of an object becomes strong enough, not even light can escape. The escape velocity, the speed required to break free, exceeds the speed of light. And since nothing can go faster, nothing escapes. The edge of this region is the event horizon, and it is the ultimate point of no return. Not because light is weak, but because the rules hold everywhere. That's the beauty of it. The constancy. No matter how deep the gravity well, no matter how extreme the condition, light never cheats. It follows the curve of space. It respects the shape of the universe. And by doing so, it draws the map of what we can know. So even when light seems to flicker, or delay, or disappear, it is still there, still moving in its way, still obeying the rhythm that lets everything else unfold. If you've ever held your hand over a campfire and felt the warmth before the flames actually touch your skin, you felt the presence of invisible light. That heat you sense is not a breeze or a vapor, it's infrared radiation, a lower energy form of light, arriving at your skin just as surely as any beam from the sun. It's a gentle reminder that light is not always what we see. In fact, most of it we don't see at all. Our eyes, wondrous as they are, only catch a small sliver of the spectrum, a narrow band of frequencies nestled between infrared and ultraviolet. We call it visible light, but that word visible is more about us than about light itself. It simply means that's the portion our biology has evolved to interpret. Everything else, radio waves, microwaves, X rays, gamma rays, they're all part of the same family. They are light too, only dressed in different frequencies, each with their own stories to tell. This full spectrum, stretching out in both directions far beyond what our eyes can see, is the real language of the universe. Stars speak in it, galaxies hum with it. The earth glows softly in infrared, even in darkness. And above it all, woven like a memory into the very sky, is the whisper of the Big Bang, the cosmic microwave background, still cooling, still expanding, still arriving. Each wavelength in the spectrum carries energy in its own way. Higher frequencies, like ultraviolet or X rays, are sharper, more forceful. They can disrupt molecules, tear electrons from atoms, break bonds. That's why sunburns happen under the ultraviolet gaze of a summer sky. It's why X rays can peer through flesh and show us the bones beneath. And at even higher energies, gamma rays, born from nuclear reactions and the collapse of stars, pierce the cosmos in bursts, brief and brilliant. But all these variations still travel at the same speed. Whether it's the gentle rise of a radio wave or the staccato pulse of a gamma ray burst, light moves through the vacuum of space at that exact, unwavering pace, nearly 300,000 kilometers per second, no more, no less. This is not a preference, it's a property. It is what defines them all as light. It's strange to think that the same light that warms your cheek in the sun is made of the same stuff that races out of supernovae. That the glimmer of a candle and the flash of a distant quasar are siblings in the same vast electromagnetic family. Light is, in this way, the great unifier, threading through scales from the tiniest atoms to the largest structures in the cosmos. And among all its roles, perhaps one of the most profound is this: light is the bridge between mass and energy. This idea was quietly waiting in the equations until a man named Albert Einstein wrote it down in the simplest of terms: E equals mc squared. Energy equals mass times the speed of light squared. A small formula, but it carries a universe inside. What it tells us is that mass and energy are two sides of the same coin. That a small amount of mass contains an enormous amount of energy, because the speed of light squared is such a colossal number. It's not just a conversion rate, it's a revelation. That matter, even when still, is energy in waiting. And that energy, under the right conditions, can become mass. This is how stars shine. Deep in their cores, under pressure so intense it defies imagination, hydrogen atoms fuse together, forming helium. In that fusion, a tiny bit of mass goes missing, but it hasn't vanished. It has become energy, radiant, brilliant energy, carried away by light. That's what starlight is, not just illumination, but transformation, the burning of mass into photons, and that same principle fuels our own bodies. The food you eat is broken down, its molecules rearranged, releasing energy that was once sunlight, absorbed by plants, stored in bonds. You are powered by photons that began their journey at the heart of a star. You are, in a quiet, literal way, made of light. Even the atoms that form your bones, your breath, your blood, they were once forged in stars, in fusion's crucible. And when those stars died, they scattered their elements into space, where they drifted, coalesced, and eventually became the matter of you, the calcium in your teeth, the iron in your blood, the carbon in your skin, all once part of a stellar fire, carried by energy, shaped by time, wrapped in light. In particle accelerators, we've seen the reverse. Smash particles together with enough energy, and new matter is born. From energy, mass emerges. New particles spring into existence, fleeting sometimes, but real. This isn't science fiction. It's a daily process in our most advanced labs, and it all plays out on the same stage, under the same rule. Energy equals mass times the speed of light squared. The speed of light, then, isn't just how fast something moves. It's how much energy lives in every gram of matter. It's the scale by which the universe measures possibility. That's why nuclear reactions release so much energy. They're not chemical reactions, shuffling electrons and forming bonds. They tap into the mass itself. And because of the speed of light squared, even a tiny bit of lost mass becomes a burst of energy large enough to power cities or destroy them. In the peaceful stillness of space, these reactions play out constantly, quietly. Stars churn and convert, nebulae glow with re-emitted light, planets absorb and reflect. Every interaction is a balancing act of mass and energy, and light is the negotiator in between. Even black holes, those strange, invisible giants, emit light, but not in the way we expect. At their core, light cannot escape. Their gravity is too strong. But just outside the edge, near the event horizon, particles swirl and collide. Matter heats to unimaginable temperatures, and in that chaos, X-rays and gamma rays are born, not from the black hole itself, but from the glowing ring of matter on the brink of disappearance, the last light to escape before falling forever. Light here becomes a final goodbye, and yet it's always a beginning too. In the early universe, before atoms even formed, photons and particles were locked in a furious embrace, colliding, scattering, tangled in a hot plasma. As the cosmos expanded and cooled, the first atoms emerged. Light was released, free at last to travel unhindered. That moment, the decoupling of light from matter, is what we still see today in the cosmic microwave background. It is the oldest light in existence, not from stars, not from galaxies, but from the birth of transparency itself. A moment when the universe became visible, not because it gained eyes, but because it released its first breath of light. And that light has been traveling ever since, not paused, not slowed, just endlessly moving. It passes through us every day, subtle, faint, ancient. It speaks of beginnings, not just of time, but of knowing. It is how we understand where we came from and how we guess where we might be going. So the next time you light a candle or stare into the flame of a fireplace or gaze up at a star that might no longer be burning, remember that light is telling you something, not in words, but in its very presence. It is the final product of fusion, of decay, of energy released. It is the story of mass unraveling into brightness. And you are the witness. You are the place where that journey ends. There's a peculiar feeling that comes with watching a beam of light bend, not in a dream, but in reality. You might have seen it when you placed a spoon in a glass of water and noticed how it seemed to snap or shift where it entered the liquid. It's not the spoon that changes, of course. It's the light, and more precisely, the path that light takes as it moves from one medium into another. It bends, refracts, curves not randomly but predictably, always toward the slower medium, always with the grace of someone following the shape of a riverbed. Now imagine that same principle stretched across the entire universe. Imagine that space itself can bend, that it isn't rigid or flat, but flexible, like fabric draped across invisible scaffolding. And that gravity isn't a force pulling down, but a dent in that fabric, curving the path of everything that passes by, including light. This is the heart of Einstein's general theory of relativity. It tells us that mass and energy warp space-time, and in response, the things that move through space-time, planets, comets, and yes, even light, must follow those curves. They don't curve because they are pushed. They curve because they have no choice. Space has changed shape beneath them. This is why starlight bends around the sun. Not just a poetic image, but a real effect, measured for the first time during a solar eclipse in 1919, when the stars near the edge of the sun appeared ever so slightly out of place. Their light had followed curved space, detoured around the sun, and entered her eyes from unexpected angles. It was one of the first confirmations of Einstein's theory. The cosmos had revealed, gently and silently, that light obeys not just the speed limit, but the road it's given. And that road is not always smooth. In the presence of massive objects, galaxies, clusters of galaxies, space-time curves more dramatically. When light from a distant object passes near these massive structures, it bends along the contours, sometimes in such a way that multiple paths arrive at Earth. The result is something called gravitational lensing, a cosmic mirage where one distant galaxy appears in duplicate or stretched into arcs and rings. Sometimes it looks as though space is peering back through a shimmering loop. These illusions are not tricks. They are truths told from multiple angles, and from those angles, we can learn what is otherwise invisible. We can weigh galaxies by how they bend light. We can map the presence of dark matter, the unseen scaffolding that holds galaxies together, because it bends light without emitting any itself. Light reveals even what cannot shine. There's something gentle about that. That light, which is massless, which doesn't feel gravity in the way we do, still listens to the shape of the universe, still honors the pathways carved by mass and motion. Even when it cannot be pushed or pulled, it can be guided, like a melody following a new harmony. But what happens when the curve becomes too steep? When the mass is so dense that the space around it folds inward completely? That's when we find ourselves facing one of the universe's most haunting features, the black hole. A black hole isn't a thing exactly, it's a region, a place where space-time has been curved so deeply that beyond a certain point, called the event horizon, no path leads back out. Not for matter, not for light. Once crossed, every direction leads inward. It's not that light slows or fails. It's that the geometry of space has changed so completely, there is simply no outward path left. From the outside, a black hole is defined by its silence. It doesn't glow, it doesn't reflect, it absorbs. But just outside its event horizon, matter falling inward becomes compressed and heated. It accelerates to near light speeds, colliding and churning, and in doing so emits enormous amounts of energy, X rays, gamma rays, visible light. So while we cannot see the black hole itself, we see its shadow. We see the last light given off by things that were about to vanish. And in 2019, for the first time, we captured an image of that shadow, not with a single telescope, but with a network of observatories across the globe linked together to form the Earth-sized Event Horizon Telescope. They watched as light bent around the supermassive black hole at the heart of galaxy M87. They stitched together those bent beams, those ancient photons, into a ring, the outline of the point beyond which light can no longer escape. That image was not a photograph in the usual sense. It was a record of delay, of distortion, of the way light is curved by gravity. It was proof that even at the edge of the unknowable, light still travels the only way it can. And yet, even here, the rule holds. Light cannot outrun the curve. It cannot escape a space where the shortest path leads only inward. The speed remains the same, but the terrain has changed. Like a river trapped in a whirlpool, the water still flows, but the loop cannot be broken. It's a sobering thought, but also a beautiful one, because it means that light, which we so often associate with freedom, is still bound by the shape of the world. That even at its fastest, it does not rebel, it yields, it flows, and by doing so, it helps us understand the shape of the very universe itself. In gravitational waves, we find this echoed. These are ripples in the fabric of space, created when massive objects accelerate, especially when they spiral toward each other, like neutron stars or black holes dancing to their end. These ripples travel outward not as light, but as changes in space-time itself, and yet they move at the same speed, the speed of light. This was confirmed in 2017 when astronomers detected a pair of neutron stars merging. First, they saw the gravitational waves, gentle compressions of space passing through Earth. Then, just seconds later, they saw the light, the flash of the collision. Two messengers from the same event, traveling together across the cosmos, arriving almost side by side. Their shared speed confirmed what we hoped, that light and gravity's whispers keep pace in the same cosmic race. Why should this be? Why should light, which we can see, and gravitational waves, which we can only measure indirectly, travel at the same rate? Because the universe has one rhythm, one maximum, one beat. Whether it's light, gravity, or information, the cosmos has chosen a tempo, and everything, moves in time with it. That rhythm is what allows us to understand, to measure, to know, and to dream. Even now, as you lie still in the quiet, the photons that touch your skin, that pass through your window, that reflect off the walls, each of them is shaped by these cosmic rules. Some may come from your lamp, some may have left the sun minutes ago, others longer still. They move, all of them, through a world that curves, a world that flows. And in that flow, we find a truth so soft it almost disappears into the hush of night. Light does not resist the universe, it reveals it. If you lean far enough into a question, sometimes the universe leans back. You ask it quietly, from beneath the blankets of your bed or the canopy of stars above. What if something could go faster than light? And though no voice replies, a soft wind of wonder brushes past, because that question has been asked for as long as we've known how to watch the sky, not just by scientists, but by dreamers, by storytellers, by anyone who's ever looked at the vastness of space and thought, there must be more. To imagine something faster than light is to imagine breaking the most sacred rule in the cosmos. But we still imagine it. It begins with a thought, quiet and curious. What would it mean? Could we send a message into the past? Could we travel across galaxies in the blink of an eye? Could we bend space and time not just in theory, but in practice? The first thing to understand is this: nothing we know of, nothing with mass or energy, has ever gone faster than light in a vacuum. Not once. Not in any corner of the universe we've explored. Light's speed is not just the fastest, it's the foundational speed. Every calculation we make, every equation that holds the universe together, assumes this limit. And yet, tucked within those very equations, like lullabies humming from the heart of physics, are possibilities, mathematical whispers of particles that might move faster than light. We call them tachyons, hypothetical, never observed, but not forbidden by all versions of the math. In theory, a tachyon could never slow down to light speed, just as we can never speed up to it. It would always remain on the other side, unreachable from our reality. If it exists, it sees our world from the far shore of a river we can't cross. The idea is strange. The consequence is stranger. If something could move faster than light, then in some reference frames, it could arrive before it was sent. Cause and effect could flip. A message could reach you before it was written. The future could echo backward, altering the past. And suddenly, time, our most trusted companion, would no longer be a steady path. It would be a tangled web. To preserve the order of things, the universe seems to have chosen restraint. It lets us imagine these possibilities. It lets the math explore. But in the real world, in the lab, in the stars, in the pulse of every photon, we find only compliance. No particle, no beam, no wave has ever been caught exceeding the limit. And so the speed of light remains, not as a prison, but as a promise. Still, the mind drifts. What if, instead of trying to move faster, we changed the rules around the journey itself? This is where ideas like wormholes and warp drives emerge, not from fantasy, but from the outer edges of general relativity. A wormhole is a tunnel through space-time, a shortcut between two distant places. Not faster than light travel exactly, but a way of shortening the distance light would otherwise need to cross. If you could fold the fabric of the universe, bringing two distant points together like pages in a book, then a traveler might cross in an instant. The concept was first imagined by Einstein and Rosen in 1935, a bridge between two regions of spacetime, now called the Einstein-Rosen bridge. But maintaining such a tunnel would require something extraordinary, exotic matter with negative energy. Not just rare, but entirely theoretical. No one knows if such a substance exists. It's a placeholder in our equations, like a dream yet unshaped. Similarly, the idea of a warp drive comes from imagining space itself contracting ahead of a ship and expanding behind it, moving the ship without the ship itself accelerating. The Alcubierre drive, named after physicist Miguel Alcubierre, plays with this concept. In the equations, it's possible, but the energy required is beyond astronomical, perhaps more than the mass of the observable universe. It's not impossible, perhaps, but it is deeply, stubbornly improbable. And so we return gently to what is known, to what is felt, the constancy of light, the patience of its arrival, the clarity of its rules. Because while nothing has broken the speed limit, some things come close, very close. In particle accelerators, protons are pushed to 999.999% of light speed. They circle miles of vacuum tunnels, their mass increasing, their time slowing. To them, the journey is short. To us, it spans measurable seconds. And yet, even at this edge, the barrier holds. It cannot be crossed, not with more energy, not with clever tricks, not with all the force in the universe. But sometimes we are shown shadows of what it might look like if it could. In quantum mechanics, there are phenomena that seem instantaneous, like entanglement, where two particles remain mysteriously connected across vast distances. Change one, and the other responds, not later, not even at light speed, instantly. Einstein called it spooky action at a distance, and it is spooky. But again, no information is transmitted faster than light. You cannot use entanglement to send a message. You cannot cheat causality. The universe lets the correlation exist, but holds the line on communication. Even in quantum strangeness, the rule remains. The same is true for quantum tunneling, where particles sometimes appear to jump through barriers, arriving on the other side faster than expected. It feels again like a cheat, but the statistics preserve order. No measurable signal outruns the limit. The illusion is not the law. It's as if the universe allows mystery, but never contradiction. It invites curiosity, but guards coherence. And perhaps that's the most generous thing of all, that while the speed of light is a limit, it's also a language. Everything that moves, that changes, that interacts, it does so by speaking the dialect of light. A photon from a star, a gravitational wave from a distant merger, a pulse from a satellite. They all arrive in order, singing in time. Even in the early days of Earth, long before life could see, light was shaping the world, warming the oceans, triggering chemistry, nudging molecules toward complexity. And when eyes did evolve, when creatures first turned toward the sky, they did so to receive that light, not just to survive, but to wonder. And now we send our own signals outward, radio waves drifting toward distant stars, lasers bouncing off the moon, photons encoded with meaning, a hope that somewhere, somewhen, someone might hear us. And in sending those beams, we speak in the only speed the universe will allow. So when the idea of going faster stirs in your chest, let it. Let it wander, let it explore, but remember that the journey we have, the one paced by light, is already rich beyond measure. It binds galaxies, it tells time, it weaves history into brightness. You don't need to break the limit to feel wonder. The limit is the wonder. And as you lie here, drifting slowly toward sleep, remember this. Even your dreams travel no faster than light. They glow softly in the mind, carried by the same rhythms, the same constraints, and still they soar. There is something quietly profound in the ticking of a clock, each second a measured breath, each tick a gentle assurance that time is still moving forward. But behind that steady rhythm lies something even more precise, more elemental, a kind of timekeeping so exact that it no longer relies on gears or pendulums or springs. It relies on light, or rather, on the unwavering speed at which light travels. The clocks we now trust most, those nestled in laboratories, orbiting the Earth, guiding your phone's sense of place, are atomic clocks. And their heartbeats come not from anything mechanical, but from atoms themselves. Inside each one, electrons jump between energy levels, absorbing and emitting light in the process. This light, this photon, has a frequency so regular that it can be counted. A cesium atom, for instance, ticks out over 9 billion cycles per second. That rhythm becomes a second, not by tradition, but by nature. And how do we know how far light travels in that second? Because of its speed. That fixed, universal constant, nearly 300 million meters per second, isn't just a speed, it's a ruler, a clock, a foundation. In fact, our very definition of the meter is based on light. 1 meter is the distance light travels in a vacuum in 1/299th of a second. We don't measure light's speed anymore. We use it to define what measurement is, which means that every ruler you've ever held, every measurement you've ever trusted, every blueprint, map, or architectural drawing, all of them are tied in the most quiet and elegant way to a photon, a tiny packet of light moving through the vacuum, pacing out the world. This is not just clever science, it's a kind of poetry, that we use something so intangible to define things so concrete, that the speed of something we can't touch or hold becomes the bedrock for bridges, for satellites, for cities. It's as though the universe handed us a universal standard, hidden inside the gentle flicker of starlight, and those standards ripple outward. GPS satellites circling above us carry atomic clocks on board. They constantly broadcast their position and the exact time. Your phone receives these signals and calculates how long they took to arrive. From those tiny differences in timing, fractions of a microsecond, it triangulates your location. That's how your map knows where you are, not by guessing, by measuring light's travel time, by listening to its rhythm. But the system only works if we account for Einstein's insights. The satellites are high above Earth, where gravity is slightly weaker, so their clocks tick a little faster. They're also moving quickly, so special relativity makes their clocks tick slower. Both effects matter, both must be corrected. If we ignored them, GPS would drift kilometers off every day. What saves it? The constancy of light. The fact that we know exactly how far and how fast it must go. We have, in a way, turned the universe's oldest traveler into our most trusted guide. But that guide doesn't just help us find our way. It helps us understand where we are in time, and even where we've come from. In distant galaxies, light stretches as it travels, redshifted by the expansion of space. That stretch carries information about distance, about motion, about age. We can see galaxies as they were billions of years ago, simply by measuring how much their light has shifted, and we can see how fast the universe is expanding now compared to how it was long ago. Light becomes not just a messenger, but a historian. In pulsars, dead stars spinning with incredible precision, light pulses arrive like clockwork, so exact that even the smallest irregularities in their timing can reveal the presence of orbiting planets, of gravitational waves, of subtle bends in spacetime itself. These pulses, these lighthouses of the cosmos, travel at light speed, carrying with them a tempo so steady it can rival any man-made clock. And at the edges of the visible universe, the oldest light still hums, the cosmic microwave background That faint glow from when the universe was just a baby is now stretched thin, chilled, but still perfectly in tune. We can read tiny fluctuations in that glow and trace the seeds of galaxies. We can measure its uniformity and test our models of the cosmos. And all of it, every pixel of that ancient light, traveled here at the same speed, from the beginning until now, unwavering, trustworthy, patient. It is light's patience, perhaps, that teaches us the most. It doesn't rush. It doesn't change its pace to suit our desires. It simply moves forward. And in doing so, it grants the universe a structure, a rhythm, a boundary. That boundary is more than physical, it is philosophical. It defines what can be known, what can be influenced, what can be shared. You cannot affect something beyond your light cone. You cannot send a message to a star faster than your photons can travel. You cannot witness an event before its light has reached you. These may seem like limitations, but they are, in truth, the fabric of reality. They make things local, understandable, ordered, and yet within those boundaries, a profound freedom. The freedom to explore, to build, to synchronize, to measure. Time, as it turns out, is not a universal experience. It is shaped by speed, by gravity, by perspective, but light gives us a common thread, a way to compare, to calibrate, to agree. Even in your own body, rhythms echo this trust in light. The rods and cones in your eyes react to photons, triggering chemical cascades that become perception. Your brain interprets those signals in time. Your memories are built from sequences, events tied together by light's arrival, woven into stories by your mind. And though you may never see it this way, your very sense of now is built on delay. The sunlight you feel is minutes old. The light from the room around you takes nanoseconds to reach your eyes. Even the signals in your nerves take time to travel. But because light is constant, those delays are predictable. And in that predictability, your experience of the world becomes seamless. So when you blink, when you glance across the room, when you lift goodnight to someone you love, you are tracing paths that photons have taken. You are not just moving through space. You are participating in the flow of information, bound together by the delicate threads of light. That wave, that reflection, that shimmer, all of it is light arriving in perfect timing. And because it always moves the same way, no matter how fast you're moving, no matter how strong the gravity around you, it gives reality its shape. Light doesn't simply show us the world, it defines the edges of what we can know, when we can know it, and how we can share it with someone else. Even our most cherished rituals are wrapped in light, a candle lit in quiet remembrance, a sunrise watched in silence, a photograph capturing a moment forever with a burst of light frozen in time. And beneath those gentle images lies the same principle. Light moved, was shaped by what it touched, and was captured before it continued on its path. Sometimes we imagine a universe where there is no limit, where messages travel instantly, where stars blink into view the moment they form, where distances vanish with the push of a button. It's tempting. It would be faster, more efficient, but it would also be chaotic. The delay we so often wish to erase is the very thing that makes meaning possible. Without light's finite speed, we would lose sequence, and without sequence, we would lose story. Think of music. Its beauty comes not from all the notes playing at once, but from their order, from the way each tone arrives after the last. A song needs tempo, and so does time. The speed of light is the universe's tempo, not too fast, not too slow, just right to make memory, anticipation, understanding. And there's something profoundly comforting in that. That no matter how far apart we are from someone else, on the other side of a planet or a galaxy, there's a rhythm we share, a rule we both obey. Light will always take a certain time to travel. You cannot speed it up with longing, but neither can anything slow it down with distance. So when you look up at the stars and wonder if someone out there is looking back, remember, if they are, they're seeing you as you were, just as you're seeing them as they were. The present in this universe is a negotiation, a meeting point between two pasts connected by the bridge of light. That bridge is what lets us send signals to rovers on Mars, to spacecraft sailing past Pluto, to telescopes watching the edges of space. It's what allows a surgeon to guide a robotic hand across an ocean, or an astronaut to speak with a voice delayed by seconds but clear as breath. It is the same bridge that allows you to see your own reflection, just fractions of a second behind the real moment. The world is not instant, and yet it is always in motion. Even your dreams, drifting slowly across your resting mind, are shaped by delays. The light that once entered your eyes becomes a memory. The glow of a fire, the sparkle of snow, the trace of sunlight through leaves. All of them recorded by the steady arrival of photons stored by the brain, reimagined at rest. And in this quiet space between perception and imagination, the speed of light still matters. It defines not just the edges of physics, but the texture of experience. It sets the pace at which the universe reveals itself, not all at once, but gently like a story whispered in chapters. So as you sink deeper into stillness, let yourself be held by that rhythm. The same rhythm that moves planets in orbit, that carries the warmth of the sun to your skin, that brought you the first glimpse of a distant galaxy when you were a child. It's the rhythm that time itself seems to follow. A rhythm without hurry. A rhythm that simply is. And in the hush of that constancy, there is peace. Somewhere beyond the fields and cities and orbiting machines, light moves through the empty vastness, not with urgency, but with grace. It glides, not knowing where it will end, not burdened by purpose, yet always fulfilling it. And sometimes in that long passage across the dark, light fails to be enough. Not in its strength, but in its reach. There are places, now and always, where light simply cannot go. There are moments when we must listen beyond it. Because though light is the fastest thing we know, the most reliable messenger in our grasp, it is not the only voice the universe uses to speak. There are others, quieter, subtler, deeper. Some are only now being heard. Neutrinos, for example, tiny ghost-like particles that pass through matter as though it isn't there. They come from nuclear reactions, from the hearts of stars, from the explosions that end them. They travel at nearly the speed of light, barely interacting with anything, slipping through the earth like whispers through fog. And when light is blocked, absorbed, or delayed, neutrinos arrive first. Silent witnesses to events that light must work its way around. In the supernova of 1987, neutrinos reached us before the light did. Bursting from a collapsing star 25 times the mass of our Sun, they passed through the star's outer layers and into the cosmos long before photons could escape. Telescopes would later confirm what neutrino detectors had already begun to murmur. A star had died, and the universe had whispered it before it shone it. But neutrinos still obey the limit. They do not outrun light's potential, they simply escape sooner. Light is often trapped in dense matter, absorbed and re emitted over and over again, slowed not in speed but in path. Neutrinos, untouched, flow straight through, not faster but freer. And then there are gravitational waves, ripples in the very fabric of spacetime. Born from the spiraling embrace of massive objects, they pass through everything, stars and planets, us, without resistance. They do not shine, they do not reflect, they only stretch and compress ever so faintly as they pass. It took us a century to hear them, and when we did, it was a revelation. Not because they told us something new, but because they confirmed what we had only imagined, that space itself can move, that light is not alone in its motion, that the canvas can ripple, not just the paint upon it. Still, those ripples, too, move at light speed. They are not shortcuts, they are not cheat codes, they are echoes of motion, carried at the same pace that light has always known. And so again, the boundary remains. Nothing we have found breaks it. Every new signal, every new particle arrives in step. But as we reach for fainter and more ancient signals, light becomes harder to hear. Dust clouds hide newborn stars. Galaxies drift so far that their light stretches into wavelengths too long for our eyes. Some radiation from the earliest moments of time, before atoms, before stars, lies so far beyond the visible that only the radio telescopes can detect it, and even they must strain. There are places, then, where light is not enough, not because it is weak, but because it is veiled, scattered, stretched, absorbed. And in those places, we must learn to see differently. In the centers of galaxies, where supermassive black holes feed, the light around them is torn and twisted, distorted by gravity and motion. But there too we find new ways to observe. Radio waves, X-rays, polarizations, all of them extend the reach of our senses, reminding us that light, though singular in speed, is plural in voice. Even darkness is not truly empty. The night sky, once thought to be black because of a finite universe, is instead filled with light too stretched to see. Olbers's paradox, that the night sky should be bright if the universe is infinite, is answered by cosmic expansion. The light is there, but the universe has grown so vast that its photons have cooled, slowed in frequency, stretched beyond the bounds of our detection, not vanished, just softened into invisibility. And still, they travel. And so we begin to think differently, not just in light, but in data, in signals, in imprints. A planet orbiting another star dims its parent's glow for just a moment, a transiting shadow, a flicker in the brightness. Not light itself, but its absence tells us a story. A wobble in a star's motion, a subtle shift in spectrum. Those are indirect signals, but they are real. Light, then, is not always the event. Sometimes it is the evidence, and in some places, even that evidence fails. There are regions of the universe from which no light will ever reach us, not because it is slow, but because the universe is expanding faster than light can bridge. Galaxies beyond a certain distance are receding not through space, but with space. The fabric stretches so quickly that their light will never arrive. We can calculate where they are. We can estimate what they once were, but we will never see them, not even if we wait forever. This boundary is called the cosmic event horizon, and it is, in many ways, like the horizon of a black hole, a limit not of motion, but of knowing. Light can only show us so much. Beyond that, there is silence. And yet, what we do see is more than enough. The sky is full of light that has traveled across billions of years, crossing epochs, civilizations, and changes no eye could predict. Light that began before the earth cooled, before the moon formed, before the first tree or the first thought or the first name for light was ever spoken. And somehow it found its way to you. This is why astronomers speak of deep time, because the light we observe now isn't just distant, it's ancient. Each photon carries a piece of a moment long past, preserved in motion. It is not a replica. It is the original. It has not aged. It has not forgotten. It is the past, still unfolding. And when we catch that photon, when we measure its energy, its direction, its shift, we are not seeing what was. We are seeing what is. The light does not know how long it has traveled. It only knows that it arrived. In this way, light transcends memory. It is the memory. And while it may not be the only signal the universe has to offer, it is the one we have listened to the longest. It is the thread that ties our earliest stories to our latest discoveries. It is the ink in the book of time. So when it seems not enough, when darkness spreads, when signals weaken, when noise obscures the message, it helps to remember that light has never failed. It has only ever been delayed, redirected, stretched. It is still coming, and even when it cannot be seen, even when it is outshone or outpaced in some narrow way by particles or waves or shadows, it remains the rhythm we trust, the measure of what is real, because while there are other voices in the universe, it is light that taught us how to listen. Even now, as your breath slows and the hush of night settles softly around you, the light continues. Somewhere out there, far beyond your window, photons are still in flight, leaving stars that were born before your ancestors ever dreamed, weaving through dust, curving along the gravity of worlds they'll never touch, heading toward eyes not yet opened. Light has no destination in mind. It simply goes, and in going, it becomes the silent storyteller of the cosmos. Perhaps that's what makes it so gentle, even as it carries the weight of the universe's secrets. It never insists, it never rushes. And yet, by its constancy, it shapes everything, from the first glow after the Big Bang to the faint shimmer that defines a teardrop in candlelight. Light moves with a patience so complete, it seems eternal. And as it moves, it measures, not just distance, but transformation. For light is not merely a traveler, it is a witness. It watches stars ignite and fade, galaxies collide and stretch, atoms dance in heat and silence. Each photon holds within it a record of its last interaction, a spin, a frequency, a path. By the time it arrives at your eye, it has been sculpted by the universe itself. And what does the speed of light truly tell us in the end? It tells us that the cosmos is connected, but not tangled, that no event happens all at once, everywhere, that the universe unfolds moment by moment, frame by frame, so that it can be seen, felt, understood. Without this limit, there would be no causality, no narrative, no memory. Time would collapse, but light keeps it from doing so. By moving at this particular speed, it allows space and time to trade places as needed. It allows the fabric of reality to stretch and bend, but not to break. It keeps the past behind, the future ahead, and the present as a soft, passing edge. And that edge, where light arrives, where it touches you, is where everything becomes real. Think of how the Earth moves around the sun, not in a perfect circle, but in an ellipse, spinning, tilting, leaning slightly like a child nodding off in a warm chair. With every tilt, every orbit, the light that touches our planet changes. Winter and summer, dawn and dusk, shadows shifting as if the world itself is breathing. None of this would be possible without the speed of light setting the tempo, delivering the sun's warmth at a delay so perfect we never feel it. But we're not just passengers in this rhythm, we are participants. Our hearts beat in time with the day. Our eyes open and close with the arrival and retreat of light. Our cells rise and rest with the cycle of its presence. The circadian rhythm, the inner clock that tells you when to sleep, when to wake, is calibrated by the sun. And the sun's light, ever steady, ever returning, makes sure that rhythm continues. Even dreams, those strange flickers of thought and sensation, are painted with images brought to us by light, not in real time, but in memory, in reconstruction. A face you saw under morning sun, a hallway drenched in evening amber, a shimmer on water that never left you. Light lives in those dreams, not because it is present, but because it was. And maybe that's what matters most, that even in its absence, light leaves something behind, a mood, a shape, a feeling. It leaves warmth on the pillow after you've turned away. It lingers on your skin long after a sunlit afternoon has faded. It leaves ghosts on your photographs, traces on your retinas, echoes in your memories. And when you sit in darkness, waiting for something to arrive, light always does. Even in the deepest depths of space, where no star shines nearby, you find the glow of galaxies stretched so far that their light is barely more than a whisper. Yet still it comes, not to illuminate, but to remind us that time flows forward, that motion matters, that we are, in every breath, a part of something vast and quietly astonishing. All because nothing can go faster than light. Not because the universe couldn't have chosen a different rule, but because this particular rule, gives structure to the unfolding of everything. Without it, events would blur, meaning would be lost, but with it, we have past and future. We have signal and silence. We have the space to dream, to wonder, to wait. We often think of speed as aggression, as competition, as force. But light's speed is none of these. It is not the fastest because it traces. It is the fastest because it simply is. And in being so, it holds the line that lets everything else slow down. Everything else take shape. Even now, in the circuits of the device you're reading on, light is moving. In lasers, in fiber optics, in semiconductor junctions, photons bounce, reflect, are absorbed and re-emitted. They carry your thoughts across networks, your voice across oceans. They carry this very sentence from code to meaning. And still, through all this, through every photon, every echo, every spark, light moves at the same pace, steady, trusted, kind. It does not leave anything behind in a hurry. It does not abandon. It offers itself completely, and then moves on without looking back. And perhaps, in this way, light teaches us the most gentle lesson of all, that motion is not always escape, that speed is not always violence, that change, when done with grace, can be a kind of illumination. So when your eyes begin to close and the room folds into darkness, remember this. You are not falling into absence. You are falling into a world built by light. into a rhythm that will continue long after you sleep. The stars will still shine. The galaxies will still send their messages. The photons will still arrive, one by one, painting stories into the silence. And you, resting here, are part of that story. You are a point along a beam that began long ago and will continue long after. And though you may not see it in this moment, though your eyes may soften into dreams, light will keep moving, gently, endlessly, exactly as it must.